Welcome to this NPTEL lectures on robotics, basic and advanced concepts. In the last lecture, we had looked at force control of manipulators and also how to design or implement a hybrid position force control of manipulators. Okay, so in this last lecture of this week, we look at some advanced topics in nonlinear control of manipulators. So the first advanced topic which we will look at is stability. Okay, a word of warning. So in this last lecture, we will not be doing too much mathematics. Okay, but I want you to introduce to some of these advanced topics like stability, controllability, and so on for manipulators. These are sort of very well understood for linear systems, but what can we say about stability and some of these advanced topics for nonlinear robots? Okay, so let's start with stability. So first, what is the definition of stability? The most widely accepted definition of stability is that if you give a bounded input to a system, the output is bounded. Okay, if this happens, the system is said to be stable. Okay, in a linear controller, this is very easy to analyze. Okay, remember for the single link manipulator under proportional control scheme, I showed you that if I give a step input, which is a bounded input, the output omega t, which is the speed of the link of the robot, approaches omega dt as t tends to infinity. It was an exponential curve. It did not go off to infinity, but it approached omega d, which was the step input. So the proportional controller can be said to be stable. PD controller is also stable. Okay, we can show that. However, the PID controller is not necessarily stable. Okay, a PID controller can make a stable system unstable. Why? Because the I introduces a term like Ki divided by S. So if you have a second order system and if you have a I part, an I controller which you add to it, it will become a third order system. And third order systems, you can show that it can become unstable. So basically, those of you who have done a course in controls, we can plot the root locus. We haven't done this in this robotics course, but we can plot the root locus of a third order system and show that for certain gains, the root locus go onto the right half plane. Okay, so PID controller can make a stable system unstable that way if you don't choose the integral grain properly. Nonlinear controllers are very difficult to analyze for stability. Okay, there are very few general results available. So the most well-known way to do stability analysis of a nonlinear controller, or for that matter any nonlinear system, is using what is called as Lyapunov method. Okay, so we will look at this Lyapunov method in a little bit detail. The last topic which we will look at is controllability. So even if the system is unstable, okay, how do we know we can control this nonlinear system? So let's look at stability analysis using Lyapunov's method. First, a little bit of history. Lyapunov was a very well-known Russian mathematician in late 1800s. Okay, think of it, more than 130 or 140 years back. He did his work. And he presented one of the few general and widely used results for nonlinear systems. Okay, how to analyze stability for nonlinear system. This was presented in 1892, so more than 120 years back. And there has not been that much improvement of his results. Okay, so let's continue a little bit. So if you have a nonlinear system, which can be described in this form, x dot is equal to f of x comma t. So x is an element of r-dimensional space. F of xt are n vector functions. T denotes time. Okay, so we can only look at systems which can be x dot is equal to f of xt. There is no nonlinearity in the x dot. Okay, there is nonlinearity in x. So f of xt could be a nonlinear function of x and time. Okay, so this ODE has a unique solution starting at a given initial condition. Okay, so this is an ODE. If I give you an initial condition, I can at least conceptually integrate, definitely integrate numerically, and find what is x at every time instant. Okay, so this is the context of Lyapunov stability. Okay, moreover, in robot manipulators, there are no explicit dependence of time. So we will be left with only x dot is equal to f of x, slightly simpler than x dot is equal to f of x comma t. So what did Lyapunov say? He said that the stability analysis is to be performed at what are called equilibrium points or states. Okay, so what is an equilibrium point? Xc is called an equilibrium point or state when it satisfies f of x equal to 0. So basically x dot is 0. Okay, so we can solve this nonlinear algebraic trigonometric equations and obtain the solution which satisfies f of x equal to 0. Okay, if not analytically, definitely numerically. The interesting thing is f of x equal to 0 can have more than one solution. Okay, it's a nonlinear equation. Okay, so for example, if you say sine of x equal to 0, x could be 0 or n pi. Okay, so n could be 1, 2 and so on. So it can have more than one solution. And what did Lyapunov say? He said you need to investigate stability at all equilibrium points, at all possible solutions of this f of x equal to 0. So in contrast to a nonlinear equation, if you have a linear equation which is x dot is equal to a of x, a times x, where now a is a matrix of constant variables, it is non-singular. So what are the equilibrium points of a linear system? Only x equal to 0, because if a is regular, it is non-singular, ax equal to 0 is satisfied only when x equal to 0. Okay, so there is one equilibrium point for a linear system, whereas for a nonlinear system, I can have more than one equilibrium point. Okay, so now what is Lyapunov's second method? So this is the statement of the Lyapunov second method to obtain the stability of a nonlinear system x dot equals to f of x. Okay, so what is the statement? A nonlinear system x dot equals to f of x is said to be asymptotically stable in the sense of Lyapunov if there exists a positive definite differentiable scalar function of the state variables denoted by v of x, with v dot of x being negative definite. Okay, so let's go over this statement once more. If I have a nonlinear system represented by x dot equal to f of x, we can say that this is asymptotically stable if there exists a positive definite differentiable scalar function of the state variables x. Let us denote that by vx, and the derivative of v dot of x with respect to time must be negative definite. So this must be positive definite and v dot of x must be negative definite. Okay, just quickly go through what is a positive definite function and a negative definite function. A function f of x is positive definite if fx is 0 for all x not equal to 0 and is 0 only when x equal to 0. Okay, so it's typical example. So if f of x is x1 square plus x2 square, it is positive definite. Okay, because it will be always be greater than 0 and will be equal to 0 when x1 equal to x2 equal to 0. F of x equal to x1 minus x2 whole square is not positive definite. Why? Because this can become 0 when x1 is equal to x2, not equal to 0. So for example, x1 can be 1 and x2 is also 1. So x is not 0, nevertheless f of x is 0. But these are called positive semi-definite. Okay. F of x equal to minus x1 square plus x2 square is negative definite. Okay. So the motivation of Lyapunov's theorem comes from the spring mass damper system. So we know that with some damping, a spring mass damper system is stable. Why? Because if you displace the mass, after a while, due to damping, the amplitude will die down. Okay. So in the case of a spring mass damper system, the energy of the system is positive definite. Okay, the kinetic energy is half kx squared, right? The energy also decreases continuously with time, okay, when there is damping. So that is what E is positive definite, but rate of change of E is negative. Okay, so based on this intuition, he said that this can be extended to any nonlinear system x dot is equal to f of x, and we can find if it is stable if there exists a v of x which is positive definite and v dot of x which is negative definite. Okay, this is one of the very funny theorems, which is that it is a sufficient condition for stability. Okay, not a necessary condition. Okay, what do I mean by that? If you can somehow find a single v of x greater than 0 such that v dot of x is less than 0, it guarantees asymptotic stability. Okay, however, let's assume that you found a v of x which is greater than 0, but v dot of x is not less than 0. We cannot say that the system is not stable. Okay, so the negation of v dot of x less than 0 does not imply unstable system. All it means is that you did not make a good choice of v of x. You have to try v of x some other one. Okay, so the Lyapunov stability theorem is for stability. It says nothing about the instability or the unstable nature of a system. So we can find a system is stable if v of x is greater than 0 and v dot of x is less than 0. But if we do not find v dot of x less than 0, then it does not mean it is unstable. Okay, that is why it is called as a sufficient condition for stability, not a necessary condition. Okay, so if v of x is greater than 0 and v dot of x is less than or equal to 0, means that it is not negative definite, we can still show asymptotic stability under certain conditions. I'm not going to go into this. Okay, in the 60s, early 60s, these two researchers showed that under what condition, if it is semi-definite, what happens. What are some of the other features? It is a local result. Okay, so we are going to test for stability at some equilibrium point. Okay, so basically, if any trajectory starting in a region around this equilibrium point converges to xc as t tends to infinity, this is known as asymptotic stable. Okay, but we have no idea of saying how big is this region from where we can start. Okay, so this region of asymptotic stability or the domain of attraction is much more difficult to obtain. Okay. The next point is this Lyapunov's method is also applicable for non-autonomous system when x dot is equal to f of xt, but we are not going to go into that. So we can also determine stability of non-autonomous system. Basically, non-autonomous systems are those where we have explicit dependence on time. Okay. So the bottom line in using Lyapunov stability theorem is how to find appropriate Lyapunov function v of x. Okay, if you find v of x and its time derivative satisfying less than 0, okay, then our job is done. So let's look at some examples. So we discussed this single link robot when we were doing this control. This is even simpler. We don't have I anymore, so we have a link with a mass at the end. There is a θ1 rotation, there is a torque. Okay, gravity is acting this way. This distance is L1. The link length is L1. So the equation of motion of this one link robot can be shown to be theta1 double dot plus g by L sine theta1 is measured from here, is equal to u of t, where u of t is tau1 divided by m1 L1 square. Okay, so we can derive this. This is not at all hard, it is very easy. So I have to first write this second order differential equation in the state space form. The state equation in this case can be x1 and x2, which are nothing but theta1 and theta1 dot, and x1 dot is equal to x2, x2 dot is ut minus g by L sine x1. So these are the state space equations. So what are the equilibrium points of this system? To obtain the equilibrium point, we have to set f of x equal to 0. So u is 0. So basically we have x2 is equal to 0 and g by L1 sine x1 is equal to 0. So basically g by L1 sine x1 equal to 0 means x1 is theta1. So theta1 is 0 or theta1 is pi and theta1 dot is 0. Okay, so we have two equilibrium points, which is 0 comma 0, which means this is coming all the way down, and then pi comma 0 when the link is vertically upwards. Okay, this is vertically downwards 0 comma 0, vertically upwards is pi comma 0. Okay, so let's investigate the stability at theta1 equal to 0 and theta1 dot is also equal to 0. So the one possible candidate Lyapunov function is the kinetic energy of this system. So V of x1 is half L1 theta dot square plus potential energy m1g 1 minus cos x1. Okay, so the candidate Lyapunov function is the total energy of the system, kinetic plus potential energy. Okay, so we know that the total energy will always be greater than 0, and it is 0 only when x1 equals to x2 equal to 0. Okay, so it is a positive definite function. The derivative of this v of x1 comma x2 at theta1 equal to 0 can be obtained, and we can see it is equal to 0. Okay, so you will get some m1 L1 square x2 into x2 dot, then sine x1 into x1 dot. And what do we do with x1 dot and x2 dot? We use the state equations and we substitute the state equations here. So the derivative is not less than 0. So strictly speaking, it is not asymptotically stable. Okay, does it make sense? Yes. So if I perturb this bob by some angle and leave it, it will keep on oscillating. It will not go to the equilibrium point, which is vertically downwards. Okay, now let's consider we add some damping at the joint. So basically we say that there is a damping which is like c theta dot, so which is like minus c x2. So now my state equations are x1 dot is x2 and x2 dot is g by L1 sine x1 minus c x2. Okay, so for the above state equations, again we can use the same v and we can obtain v dot. And we can see that the v dot is m1 L1 squared c x2 squared. Okay, so this is a square. So this is less than 0. Okay, so the single link manipulator with damping is asymptotically stable. Okay, let's continue. Now let's assume that we are applying a torque to this robot, and this is the proportional control torque. So this torque is equal to Kp into some x1 desired minus x1. Okay, and Kp is greater than 0, and x1d is some desired theta1. Okay, so we can show that u of t is Kp x1d minus x1 divided by m1 L1 squared. Okay, so for simplicity, we investigate the stability at x1 desired equal to 0. Okay, is that very serious? No. If x1 desired or theta was some other angle 45 degrees, we can do a change of coordinates. Okay, and then investigate the stability at that point. But for simplicity, we'll assume theta1 desired is 0. So it is lying vertically down. Okay. So as I said, if x1d not equal to 0, we can perform a change of coordinates x1 prime, x1d minus x1 and investigate again the stability at x1 prime equal to 0. Okay. So we choose a coordinate, a candidate Lyapunov function, and again as the kinetic energy plus potential energy, but let's add one more term which is half kp into x1 square, where kp is the proportional gain. Okay, so this term is positive, this one is also positive, so the sum of these two functions is positive also, so it is positive definite. Okay, so again with state equations with zero damping, we can show that v dot of x is m1 l1 square x2 into u of tau plus kp into x1 x2, and for u of t minus kp x1 divided by m1 l1 square, v dot of x is 0. Okay, so we are using proportional controller and v dot of x is equal to 0. So again it is not asymptotically stable. So what it is telling you is, even with a proportional controller, if I give some input, it will keep on oscillating about that desired quantity. Okay. If you add damping, which is like minus cx2, again we can show that it is asymptotically stable at x1d equal to 0. So proportional controller with damping will result in asymptotic stability. Okay, so now let us consider the modified proportional plus derivative controller. Okay, so we have tau1, which is now minus kp x1 minus kv x1 dot. Okay, why am I calling it modified? Because there is no x1 desired and there is no x1 dot desired. Okay, so x1 desired equal to 0 is not a problem, we can do change of coordinates, but x1d dot desired is set to be 0. In fact, there are no, we'll see later that there are no known results when you have a desired rate of change of x1. Okay, so now let's consider again candidate Lyapunov function, which is the kinetic energy plus potential energy plus this half kp x1 square. So for the undamped system, now we can see that v dot x1 x2 is minus kv x2 square, which is less than 0. Okay, so there is no damping in the system, but there is a derivative controller. There is a derivative part of the control, and due to this derivative control, which is minus kv x1 dot, we get asymptotic stability. Okay, so as I said, x1 dot is assumed, x1 dot d is assumed to be 0. We cannot prove asymptotic stability for trajectory following when x1 d dot is non-zero. So if I tell you that the x1 desired could also have some time derivative, desired time derivative at each instant of time, there is no way to prove asymptotic stability. Okay, so it is not possible to prove stability for second equilibrium point. Remember, we said, Lyapunov said that we need to investigate stability at the equilibrium point when the link is hanging down and when the liquid link is pointing upwards. Okay, there is no way to choose v of x such that v dot of x is less than 0. Okay, we cannot prove the second equilibrium point to be stable using Lyapunov method. Why? Because we know that it is not stable. Okay, and Lyapunov's result deals with only with stability. Okay, so when the link is pointing vertically upwards, any small perturbation to the link will go away from that pi comma 0. It is an unstable point. Okay, if you linearize it, we can show that the poles of this linearized system are on the right half plane. Okay, so those of you who have done a course in control, we have looked at this inverted pendulum and we know that the inverted pendulum is unstable. Okay, recall that v of x greater than 0 and v dot of x less than 0 is a sufficient condition for stability. Okay, and theta1 equals pi is known to be unstable. So Lyapunov theorem has nothing to do with instability. This is a big thing. Many people don't understand that what is meant by a sufficient condition. How about stability of a PD control scheme for a general robot, general serial robot with n degrees of freedom? So if you don't have gravity, we can write torque as m into q double dot plus some Coriolis term. Okay, so we can have a PD controller of this form minus Kp into Qt minus Kv into Q dot T. Note again that Qd dot is 0. Qd equal to 0 is again not a serious problem because we can again do a change of coordinates. Let us consider a Lyapunov function which is nothing but half Q dot transpose mq dot plus half Q transpose kpq. What is this? If you recall, if you think back a little bit, this is nothing but the kinetic energy of the system, kinetic energy of the robot manipulator. And what is this? This is like half kp theta square. Okay, this is coming from the controller. There is no gravity, so there is no question of potential energy. We can evaluate the derivative of this v, and it can be shown by using chain rule that this is q dot transpose mq double dot plus half q dot m dot q dot kq. Okay, and it can be written as minus q dot kv q dot plus half q dot transpose m dot q minus 2cq and then q dot. Okay, so this term is negative, but we don't know what is this. This is the derivative of the mass matrix minus twice the Coriolis matrix. Okay, so it turns out that this m dot q minus 2cq q dot is q symmetric. Okay, so skew symmetric means the diagonal terms are 0. Okay, we can prove this. You can take this as a homework. You can try it yourself. If you have a skew symmetric matrix, the second quadratic form is 0. What do you mean by this? Half q dot transpose some q symmetric matrix into q dot will be 0. Okay, and hence v dot is minus q dot transpose kv q dot. Okay, but since v dot q dot can be 0 even for non-zero q, so it is not negative definite. Okay, so this is negative semi-definite. So this is like that q1 minus q2 whole square. Okay, that's similar to that case. So the function can be 0 even when q1 and q2 are not 0. Okay, however, you can show by this LaSalle and Lefschetz invariance principle that the equilibrium point q and q dot is asymptotically stable. Okay, so what have we shown? We have shown for a general n degree of freedom manipulator without gravity, without a desired rate of change of the desired trajectory, okay, this manipulator under PD control is stable. Okay. As soon as you add qd double dot or q dot not equal to 0, okay, we cannot prove asymptotic stability. Okay, so this is a very unsolved problem. So if you have trajectory tracking or trajectory following, that the desired derivative of the joint is not 0, we cannot prove asymptotic stability. Okay, there are no known methods or results for asymptotic stability. So how about stability of model-based control schemes? Again, very little can be proved about stability. Okay, so as I said, PD and exact gravity conservation cancellation. So tau is minus Kp Qt minus Kv Q dot T plus gravity G of Q. This can be shown to be stable. Why? Because the gravity is going away and we are left with the equation tau is equal to mq double dot plus Coriolis term and centripetal term, and that we show is stable. How about computer talk with exact cancellation? Again, that can be shown to be stable. Why? Because the error equation is damped linear second order ODEs. Okay, and depending on choice of Kp and Kv, we know that the errors will go down, okay, to 0. So this is asymptotically stable. So the stability analysis of general model-based control schemes, where the mass matrix is not exactly known, where the gravity is not exactly known, is still an unsolved problem. Okay, and it turns out that such systems can exhibit chaotic motions. Okay, so there are results which show that the model-based control schemes where the mass matrix and the Coriolis term or the gravity term is not known exactly, we can exhibit chaotic motions. Okay, so that is clearly not asymptotic stability. Let's continue. We also discussed that there is this lack of knowledge of model parameters in most practical robots. Okay, and hence no exact cancellation is possible, and it is difficult to predict the evolution of T. So remember, when you had inexact models, we had a linear second order system, but the right hand side was a complex quantity. Okay, there was a forcing which was not 0. Okay, so we do not know what E of T will look like. Okay, so it's a linear second order ODE, but with a nonlinear right hand side. We do not know what it will do depending on the nonlinearity. We have seen that if the estimates are good, then the right hand side is small and the E and E dot will go to 0, okay, or become small. But there are no general results of what is this range of estimates or how good the estimate should be for E and E dot to go to 0. The other issue is if you do not know the model parameters exactly, can we find it out? Okay, yes, the answer is yes. The model parameters can be obtained using adaptive control schemes. Okay, so we don't want to get into adaptive control schemes, but basically we can look at the errors and then we can have some adaptive control laws which go and change the model parameters such that the errors go to 0 over time. Okay, and at the end of this adaptation period, we will know exactly what are the model parameters. The last thing that I want to discuss is this controllability of a system. Okay, so the mathematical notion of a controllability of system is the following. Okay, a system x dot equal to f of x is said to be controllable if it is possible to transfer the system from any initial state x of 0 to any desired state x of tf in finite time tf by application of the control input u of t. Okay, so I have given you some mathematical system. How do I know I can take this system from a given initial state to a final desired state by applying torques or applying the external input? Okay, in a linear system, this is well known. People know exactly what is the result. People can predict what happens or under what conditions a system is controllable. So in a linear system, we have x dot is equal to fx plus gu. F is a constant matrix. G is another constant matrix. So n state variables with m inputs. The system is controllable if you find a matrix which is G concatenated with f into G into f square G and all the way till fn minus G. So if G is one dimensional, so first column is G. F into G will be a second column and so on. So there will be n columns. Okay. So this matrix, if it has rank n, then this system x dot is equal to fx plus gu is controllable. Okay. What about nonlinear robots? There are no known results for controllability. So we cannot say that for this robot mathematically, I can take it from an initial theta and theta dot initial state to a final theta and theta dot state using the torque. Okay, what do we know about controllability? The only thing we know about controllability and which can be proved is that a nonlinear robot is not controllable at a singularity. Okay, why? Because at a singularity, you either lose a degree of freedom or you gain a degree of freedom. Okay, and those loss and gain degrees of freedom, okay, we cannot move perpendicular to the direction or along the loss of degree of freedom, and similarly problems arise when you gain a degree of freedom. Okay, so in summary, we have discussed Lyapunov stability, and we have used Lyapunov stability to predict the stability of a nonlinear system. Okay, so there are very few analytical results on nonlinear robots and manipulators. Okay, so no stability results are available for trajectory following when theta derivative of theta d, first or second derivative, is non-zero. Okay, the lack of knowledge of model parameters can be solved to some extent using adaptive control. Okay, and finally, a nonlinear robot is not controllable at the singularity. Okay, so that is another reason why we need to know where the singularities of a robot are, because we cannot control the motion. Okay, so with this, we come to a stop of this week. Okay, next week we move on to a different topic. Thank you.